Okay, today we'll talk a few minutes about radio frequency fundamentals, and you'll be able to see as soon as the screen gets done here. Why do we care about radio frequency fundamentals?
That way we know the way they react.
The way they react, what's going to happen under certain circumstances, and why in this particular environment is something happening. We talked last time a little bit, mentioned that, and it's in one of the questions. You go in and somebody went in and put in wireless access points, got them working in the lecture hall for a college, university, and everything's working fine. And then you fill up the lecture hall with 200 or 300 people, and all of a sudden you don't have any connectivity, or you have slow connectivity, or some people have connectivity. What happened? We've got absorption of the signal by the people that are in the room. What causes that? That's the electromagnetic phenomena that we'll look at for some of these things. So the objectives explain the basic principles of radio frequency transmission, and the basic principle of radio frequency transmission is an alternating signal. That's what causes it to work. Why do we have to have an alternating signal? What causes current? I'll pick on my EET guys. Trevor, since you're here. What causes current? How do we generate electricity? Huh?
A magnetic field.
A magnetic field. Oh, what kind of magnetic field? You got to have a magnetic field and you got to have motion of some kind, don't you? Magnet, and what you have and the way we generate electricity is we have this magnetic field and we move through it, right? With the fixed field and the coils of wire. Coils of wire, think about as the antenna. So what we're going to have is some sort of a moving field or moving something or another, and we're going to use an alternating signal in order to do that, and then it's going to generate a current flow. Current flow is what really gives us all this stuff, isn't it? I mean, really, the current flow itself. The different types of analog and digital modulation, we'll look at those a little bit. I don't think that you're probably going to have to recognize some of their names, but I don't think you're going to have to be able to go in and actually do the describe how the modulation works, but we need to know what modulation is, because modulation is the way you put intelligence on that alternating signal. Without that, without some change or some method, nothing happens with those things. Units of measurement in radio frequency transmission are going to have absolutes and relatives, and the relatives are what we're going to use most of the time. We're going to call that dB, and then we're going to base it on a milliwatt, call it dBm. So don't get too hung up on that. And there's an exercise. The rule of tens and threes is a quick way to do. It's not precise, but it's a quick way to do the calculations of how much signal strength you're going to have based on what happens in the process in the path. And how radio frequency waves behave and impact the results of the transmissions, where we have absorption, reflection, refraction, those kinds of things. We'll try to set up a little demo, a really basic demo back here, because I've hooked this machine up here up to that access point in the back. We should be able to set one of those big metal boxes in front of it and block the signal, shouldn't we? Theoretically. Do we want that to happen? No. Might that happen? Yeah, I've talked about, and different materials have different ability to allow the signals to go through. Talked about before, in the back of the building, we have some difficulty getting signals back there because of the physical firewall. It was built to stop fire, so it's a big cement wall, got rebar and all that other good stuff in it. That's going to absorb the signal, block the signal absorption. And that happens as you go through air, doesn't it? As you go through air, does anybody listen to radio anymore when you're traveling? What happens to the signals as you get further and further and further away? They start breaking up, especially in AM, right? FM stays pretty consistent until it just quits, until you go out of range. Why does that happen? Why doesn't it just go forever? Terms of attenuation, right? Because it gets smaller the further you get away. The atmosphere is actually absorbing some of the signal.
Water vapor inside that.
Water vapor inside that. If it's a foggy day, it should go away quicker, right?
Signal, yeah.
All of that stuff, all of the things in the atmosphere can cause absorption, can also cause refraction.
Yep.
I know I told you guys a story in the Persian Gulf. Our surface search radar, we should go about 20 miles to horizon, 25 miles maybe. We could set up at Bahrain on some days and watch traffic in the Strait of Hormuz, which is, I don't know, 300 or 400 miles away. What do we get? We got some ducting, so it just would travel in the atmosphere without the absorption. We'd also get things they call running rabbits, which you get targets that weren't targets out there too. What causes that? All of that stuff is caused by the atmosphere. You'd have targets that just pop up, you know, pretty scary when people are trying to shoot at you too. But what caused that? All with the atmospherics. Understanding principle radio wave, important for troubleshooting LANs, the context of understanding wireless terminology. A big part of it is the terminology. What does each of these things mean? If you've had, and a couple of you had the EET, you've had more exposure to RF and generation and fields and those kinds of things. We talk about them in the networking world, but we don't really get into how these things actually work. This is a little bit, what you got to know here is how it works. When this happens, what can cause those kinds of circumstances? And we're going to look at terms, we talk about terms like multipath. Multipath means that we go two different paths. What can be the result of the electromagnetic signal? I know I'm getting ahead of myself, but these are things that we're going to do, and I got a little demo of that kind of shows what happens when that comes about. That's what fiber uses, isn't it? Multipath. Multimode fiber uses multipath. Multiple different frequencies get refracted and refracted. There's another good term, right? We'll see a picture of that here in a few minutes. Fiber refraction is what actually keeps the signal inside the fiber itself. The electromagnetic waves in this picture shows the electromagnetic wave. It has a magnetic portion of it as well as an electro portion of it, and they actually are at 90 degrees to each other. This is something that in the double E world, and Mr. Loomis was talking about, we were talking about it this morning, I didn't really ever have a propagation course. He did. He said he had a year's worth of it at Virginia Tech. Mine was more, and when you get a double E, you have specialization. Mine was in electronics. It was in different areas. But when you do these things, these are fairly complex things to try to calculate and use. And like I said, when you get done doing that, you got to figure out the stuff that doesn't count. But how do these things work? They have an electro portion and a magnetic, an electric field and a magnetic field portion of them, and they are at 90 degrees to each other. So these things and how they get propagated depends on polarization. Another new term, maybe, polarization. Which way does it get sent out? Which the orientation of the antenna basically is what you're talking about. Is it a vertical polarization or horizontal polarization? Most of the ones that we use, these little, what they call them, rubber ducks that are on the access points are going to be vertically polarized, which means the antenna sits up here and we send the signal out, basically one wavelength at a time. The electromagnetic wave, and another big picture here in a minute, but characteristics, continuous, does not start and stop in a cycle. So we have a picture here of a continuous wave. A sine wave is what this one is. There are a number of different waveforms that exist, but a sine wave continuously going. And we always show these things in, really big, long pictures. 2.4 gigahertz. What does that mean? if we had this picture. What's a giga? Cycles per second. But what's a giga? A billion. So that means that 2.4 gigahertz, that instead of having this thing spread out like this, really nice and pretty, it'd be changing 2.4 billion times a second. That's how we get our intelligence on these things. That to me, that's kind of mind-boggling that something can happen that many times in a second. But that's what it is, right? A hertz or k-hertz, or a hertz is a cycle per second, or gigahertz is a billion cycles per second, a billion changes per second. Why can we put more intelligence on the 5 gigahertz signal? It was faster by default, right? It was 54 when it came out, and the 2.4 gigahertz was 11. Why? You got more changes, you're going to put more intelligence on it. So the frequency, when we talk about throughput data rate, and I talked about in the communications world, long distance communications, the lower the frequency, the further it goes. But also, what also is a limitation. Can't put much data, not much intelligence can go on to the low, extremely low, super low frequency signals. The FM radio, stereo FM, is a higher frequency than AM, isn't it? Put more intelligence on it. Modulation is the way they do that, and multiplexing is the way they put those things on. Just like we talked about television. They did not change the bandwidth, the amount of space that you had to put signal into television signals when you went from a black and white to a color signal. They had to figure out ways to do that with modulations. What causes our wireless networks to be faster now? A number of things that they have changed in the modulation, the frequencies of modulation, multiplexing, how we actually put the signal on that particular frequency itself, and how big it is. Continuous, a cycle is from one point to the other. We go a cycle, if we go peak to peak, starting point to starting point, it's going to be a cycle. So if we go from the peak here to a peak over here, and we have this Greek symbol in here, lambda, which is going to represent the wavelength. So point to point cycle, when it completes and returns back to the starting points, is finished one cycle, one wavelength. How long are those wavelengths? And we're going to get into, look at a couple of calculations here in a minute, but we're going to find out that the things that we're using, the 2.4 gigahertz is a little less than 5 inches. Does that sound all right, Trevor?
12.5 centimeters. Whatever that is.
I know. He does it in meters, and I've forgotten what it is in meters. It's a little less than 5 inches. And we talked about it at night, but he knows the answer. What plant appendage is about 5 inches long? Pine needles. What does that mean? If you're trying to send your wireless in a pine forest, you're going to have trouble, because the right frequency is going to absorb the signal for you.
So if you live like near the lake on the west end, like on the west side of Smith Mountain Lake.
Yeah. Yeah. Oh yeah. Yeah. What are we going to do? Actually, I think that probably halfway length is what we would really be concerned with there, isn't it? But it's an oscillating signal, a sine wave. Electromagnetic waves share the same 4 characteristics. They have a wavelength, a frequency, an amplitude, and a phase. Amplitude is how much signal's on it, how much power's on it. The wavelength, what's the distance peak to peak, starting point to starting point, from one complete cycle to the other is going to be the wavelength. Amplitude, the phase is from one start point to the other, and we'll look at that in a minute, because we talk about, and I'm going to keep trying to use these terms, multipath, and we could do a multipath in here, couldn't we? We could have Jody go back there and walk straight up the aisle, and we could have Dante start here and walk to this wall, bounce off of that wall, and maybe come directly up here. Who's going to get here first?
Shortest path.
Shortest path. But when both of them get there, we're going to have the signal. What happens to that signal when we get multiple signals at the same time? And that's what the two antennas are for, and I have seen that on a test. Not this test, but on a test. The two antennas are for multipath, so that you don't get the differences necessarily on the, you get them on the same antenna, but then it can discriminate. What makes N faster? It uses multipath. It finds the strongest signal and uses it. So why can we get so much more throughput data rate? I'm trying to stay away from the word bandwidth, because bandwidth in the true definition is the high to the low. How big of an area do we have to put the intelligence on it? The 2.4 gigahertz range is 20 meg, huh? The N uses multiple paths, absolutely. Yeah, it uses, they call it path diversity. When you start hearing the term diversity, which I think is a fairly new term, diversity means that we have these things. We have antenna diversity, which means we have more than one antenna. And if you see an N machine or an N access point with the antenna, and many of them don't show the antennas, don't have external antennas. Some of them do, but you see them with 3 antennas. That's what gives you the 300 megabits per second, because we're going to have separate connections with each of those antennas, antenna diversity. But that means that we got to have what? Same number of antennas at the other end. If we have one antenna on the laptop and 3 antennas on the access point, we have 3 different conversations with 3 different laptops. But in order to get that throughput, you've got to have a single device connected to all of the antennas at the same time. Same 4 characteristics: wavelength, frequency, amplitude, and phase. Phase is the starting point of these things. And this is another. Cycles, this shows from the 0 point to a max, back through the 0 point to a minimum, back to the 0 point. When we go through all of those, we've gone through one cycle. So when we go back to the 2.4 gigahertz, that's doing 2.4 billion of those every second. How many things can you do in a second? I can't do one thing in a second. I don't know. Huh? Breathe? Probably takes you longer than a second to breathe, doesn't it?
Blink.
Blink? Maybe. Probably close. Yeah.
Well, your
Blink?
brain's doing a lot.
Huh?
Your brain's doing a lot.
Your brain's doing a lot, actually. Yeah, there's a lot of electromagnetic action going on in there, right? Yeah. But physically, 2.4 billion. I mean, we talk about cars. Cars, what have 2,000 revolutions per minute. This thing's doing 2.4 billion revolutions a second. NASCAR would like to harness that, wouldn't they?
Some cars they can go up to 15,000.
Yeah, I know, but not mine. Not mine.
How much they cost at 15,000?
Yeah, not mine. I've got a diesel. Yeah. Yeah, wavelength, the displacement between the peaks, the wavelength, peak to peak. Actually, wavelength is any point that's the same to any other point that's the same. We could go from 0 to 0 full cycle, and we would have the wavelength. Anywhere in the wave itself, from point to point. Frequencies, the rate at which these events occur, the rate of change is going to be the frequency. Hertz, cycles per second, kilohertz, thousands, mega, giga, 1,000, million, billion, on up. The wavelength and the frequency have an inverse relationship using the speed of light. So the higher the frequency, the shorter the wavelength, the lower the frequency, the longer the wavelength. The higher the frequency, the shorter the wavelength, the more the signal is going to be absorbed. That's why we say it's shorter distance. What actually happens is it gets absorbed so that it's below the noise level of the receiver, that the receiver can discriminate between signal and noise. Same thing can happen on physical cable, can it? That's what happens in an AM radio station. What happens in an AM radio station when you ever listen to it and you have 2 stations on the same frequency? What happens? As you get to the end of one and start the other one, you hear both of them, and then the second one will override the first one.
Yeah, you pick up the sideband frequencies.
It's sideband frequencies, all sorts of stuff that's going on there. So the higher frequency, shorter the wavelength, longer the wavelength, the lower the frequency. The lower the frequency, the longer the range. So high frequency, short range absorption. This is frequency wavelength. Frequency equals C over lambda. Aha. Good formula, right? What's C? Right, it says there. Speed of light. C is the speed of light, about 300,000 kilometers per second. We're going to make this easier here in a second. And lambda is going to be, the Greek signal lambda is the wavelength, F is going to be frequency. So we can calculate how long this wavelength is. This next one here puts in a little bit simpler terms. If you're going to do it in inches, 11.811 over the frequency in gigahertz. So if you have something in kilohertz, you've got to convert it to gigahertz for this formula to work, to get it in inches. In centimeters, it's 30 over the frequency in gigahertz. So whichever you want it in inches or meters, and I think all of these radio operator guys use meters because they specify frequency bands usually in meters, shortwave, those kinds of things are all specified in meters. So the 2.45 gigahertz here, which is about what we're talking about, isn't it? It's going to be 4.82 inches, 12.24 centimeters, and the 5 gigahertz is 2 inches. And if you measure the distance between these things back there, have you done that? About how far apart are those antennas on the access point? We'll have to get a ruler and see that. I'm guessing it looked like about, what, a little over 5 inches? About 5 inches, something like that? We'll take a look at that at the break. Lower frequency, higher frequency, nothing magic about that particular one. The hertz and the table, this is the same thing. Hertz, 1 cycle per second, kilohertz, 1,000, mega, a million, giga, a billion. It just gives you an idea when you talk in those terms. Amplitude is, when we talk about these, the amplitude is the voltage, how high is the signal, how much signal is on it. If we were talking in terms of voice, it would be how loud we would be, wouldn't it? If I were talking like this, it would be a low amplitude. And then the amplitude would go up. What happens to the amplitude over time? Decreases. Or time distance. Phase is the relationship between at least two signals that share the same frequency yet have different starting points. So if we started one, it's just like we talked about the multipath, which would be two frequencies. We start at one point, or if we started even coming up the aisle here, if we started one of you guys at one point and another one at the other point, that's what a phase difference would be. Different starting points in these things. And that's what happens in our multipath when we get to the endpoint. We're going to wind up with different phase. But even though it starts out as the same signal, when it gets radiated out in all directions, it gets bounced off of different things, absorbed differently, refracted differently as it goes through. So when it gets to the receiver, you get the same signal, same frequency gets there at different times. It's going to affect what kind of signal you get there. So the phase is, if the second signal is 180 degrees out of phase, we're going to get a grand total of 0. Noise canceling headsets, yeah. Because they did actually detect, yeah, they detect what's there, right? Yeah. And then they put a signal 180 degrees out of phase. I've got, while we're doing that, and it's actually about multi-path, but I got a little demo here. Okay, so this thing has got a number of signals. This is just a sine wave going from point A to point B. We have wave 1, and then we can have wave 2. These are different polarizations. One's vertically polarized, the other one's horizontally polarized. And that's what polarization means. Which way does the signal go out, vertically or horizontally? But what I want to look at here in the phenomenon is go to this exercise. Two identical vertically polarized waves are superimposed on each other. These are in-phase signals. And if we'll turn off wave 1 plus wave 2, we have, and we'll turn off wave 1, we have wave 2. Turn off wave 2, we have nothing, wave 1. So these are two sine waves that are in phase with each other. When they get there in phase, what happens to the signal?
Double.
It's double. Now we can go to one that these are 70 degrees out of phase with each other. So we're going to get some decrease in signal when all of that gets there, all of the multipath gets there bouncing around in different locations. And then we go with 140 degrees out of phase. Notice that the combined signal is now less than the individual signals. Phase difference, when do they get there at the different time start points? This was the starting point, but if you think about when it gets there, when the signals get there, that's going to be the starting point at the receive end. And then if we look at 180 degrees out of phase with each other, we still have down here, we have the wave 1 plus wave 2, but they're 180 degrees out of phase with each other, so we get a zero signal. Multipath causes this at the receive end. It is wild, even though you have those signals, but if you start them out at the same time, then they just cancel each other. It's there. You just can't get it because when they get there, when the peak, when the positive, the highest point and the lowest point add combine, you get a zero. And these things are so that at every point along the curve, the negatives and the positives are the same value, but opposite in value. Okay, so the in phase and the out of phase. This is the phase relationship. We already looked at that in the visual that we saw. The electromagnetic spectrum is a range of all the electromagnetic radiations: radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray. It's a continuous spectrum, different frequencies. Obviously, as we go through here, and this one at the bottom shows a representation of what frequency would be for those different parts of the spectrum. Table that's in the book, and I'm gonna go through. You're gonna read that, where they go and what they do, and each of these things has its own. Each of these parts of the spectrum has its own function, doesn't it? License normally required. The unlicensed bands, those are the 2.4 gigahertz and the 5 gigahertz are unlicensed bands. Good thing and a bad thing is you can go build yourself a device that works in that. The bad thing is, so can the next guy. I was doing a course one time. This was a CCNP probably course, and the instructor was talking about he was consulting with this company, and they needed to put a wireless connection between two of their buildings. So they put up the antennas, and it was going really, really good, and then it quit working. Didn't know what was happening, so they went up on to the roof of the building and found out that somebody put an antenna in front of their antenna. What can you do about it? What can you do about it? Nothing. So they had their bridge that worked for a while, building to building, and people do those things, but somebody went in and decided they needed that space, and they put theirs in. So you've got to figure out how to put your antenna, place your antenna so that you can still get the electromagnetic line of sight that you need to do that.
They have to worry about birds flying on top of the antennas.
Probably, I don't know.
Their weight.
Yeah, probably eventually. But I didn't have to worry about that on my satellite. Actually, I've never seen any birds on it. Maybe they just don't like it. Sometimes the frequencies they don't like, I think. I mean, it's kind of like that's what they're talking about with the windmills are killing all the bats. It has nothing to do with the speed of the blades, because if you've seen those things, I could probably get out of their way. But it's the frequencies that they generate that messes up the bat's sonar. FCC imposes power limits on the devices using the unregulated bands, reduces their range. And they do, and I told you the story about a guy in Colorado, and this was actually in one of the books, that decided he wanted to see his wireless access point in his favorite bar, and he built his big antenna amplifier in order to get the signal there, and then couldn't figure out why he couldn't connect to it. He didn't have the same antenna amplifier on his laptop. Just because you can see it doesn't mean that you can actually establish communication. And that's called a hidden node. If we send a really strong signal out and we have a really weak signal coming back, you can see it, but you can't get there. So those things happen. Unlicensed National Information Infrastructure, Uniband, that's the 5 gigahertz. That's the name for the 5 gigahertz. The ISM is the name given to the 2.4 gigahertz range. The different frequency range, very low, low, medium, and again, that's in the book. Just say that it is there. The unlicensed bands are right here. The one we haven't mentioned, and I think this is the one that the handhelds, the portable phones first came out on 900 megahertz on it. 900 megahertz is also an unlicensed band. What's the problem with the 900 megahertz?
Well, most cell phones use that.
Yeah, but what's the problem with that from a networking standpoint? Why don't we use that? Be longer range.
Yeah, but you couldn't put very much data.
Couldn't put much data on it. Voice works okay. So those are the ranges that are in those things. For the electromagnetic wave to transfer information, it's got to be modified. Because if that, what does a 60 cycle hum, right? You heard that term. You may have heard that term. It's just noise, right? 60 cycle hum. That's if you just set the sine wave up at 60 cycles with no intelligence. What you're going to get really is a hum, or you get some sort of a squealing frequency, squeal, depending on what frequency you're at when you hear these things. In order to put intelligence on it, we've got to modulate it. And they're going to have different modulation techniques when you go through those things. So the electromagnetic wave that's been modified in order to carry information is the carrier signal. Carrier wave or carrier signal. So the carrier signal is the base frequency that we're using these things at. Can be performed on either analog or digital transmissions. Analog, continuous signal, no breaks. The sine wave is an analog signal. Amplitude modulation, guess what? We changed the amplitude. Frequency modulation, we changed the frequency. That's why, and I go back to Jody because he said he actually listens to the radio sometimes, AM. What happens to AM radio in a thunderstorm when there's lightning? You can hear the lightning. Why is that? Electromagnetic, because it's amplitude modulated. It changes the amplitude of the signal. But you don't hear that in FM. Because it's frequency modulated. It actually puts the lightning on the signal, but it doesn't care about the amplitude. All it cares about is the frequency change. What happens if you chop that off, you actually just take that signal out when you go through the receiver itself. Phase modulation, when we change the starting points, and there are phase modulation. We're going to have some figures here, and they might expect you to know what they look like. You're not going to have to go into any detail on those, but what an amplitude modulated frequency modulated and phase modulated signal looks like. This would be the amplitude modulation. We change the amplitude. A 0 and a 1. A 0 would be a certain voltage, a 1 would be a certain other voltage when we did those things. Frequency modulation, you notice that the 0 has 1 cycle and the 1 has 2 cycles. So that would be frequency modulation. We just change the modulation itself. The one that's really strange is phase mod. But based on what we saw, that's kind of what it would look like when you change the phase, wouldn't it? Because it's going to change how much of the signal is there. But that's what a phase modulated signal is going to look like. Digital consists of data as discrete or separate, unlike analog, which is continuous. Digital is ones and zeros, on or off kind of deal. Advantages: better bandwidth, requires less power, better handling of interference from other signals. Why would it be better handling of interference from other signals? Because they're either on or off. You don't have to worry about any of the things in between, like the lightning that puts the noise on the AM. What if the lightning put noise on your digital signal? Probably not going to matter that much, is it? Unless it's a 0 maybe. Error correcting techniques, the same 3 types of modulation as analog. It's going to be amplitude, frequency, and phase for digital as well as for analog. Except they're going to have it a little bit different name, and I think I've got a chart here that's got these on it, and your modulation activity that you got is to recognize the charts, what they look like. Amplitude shift key, similar to amplitude, instead of both a 1 bit and a 0 bit having a carrier signal, a 1 bit has a carrier and a 0 bit has no signal. So amplitude, we do or we don't. Frequency shift key changes the frequency of the carrier, and the phase shift key changes the phase of these things. This is what the amplitude shift key said that if it was a 1, it had signal, right? And if it was a 0, it had no signal. So that's what an amplitude shift key signal would look like. Went too fast there. Amplitude shift key looks the same, doesn't it? Or amplitude frequency shift key looks about the same as the frequency modulation. So those are very similar. And the phase shift key looks about the same. This is from a different book, the Modulation Comparisons, the amplitude modulation, frequency modulation, and phase modulation, if you look at those things. The base signal, the baseband signal is the one at the top. Amplitude shift key, the second one. The frequency shift key, the third one. And the phase shift key, the one at the bottom. These, by the way, slides are in the PowerPoint link on your course if you ever want to go back, if you want to go back and look at any of these things. Signal measurements. This is what we care about, right? The signal measurements. We don't care about all this. Somebody else does that. Those are actually, we can see them sometimes, but what can we actually measure? If you look at signal strength, right? dBm, and you see these things, and when you get it, it says something like minus 80 dBm. What does that mean? You got an exercise, the rules of 10s and 3s, and we're going to go through that in a minute. Activity that you have goes to that. You're going to make a chart basically relating dBm to power. And that's all they are. dBm means that we start with 1 milliwatt and we go up or down. So we have milliwatts, dBm, decibels, milliwatts. We haven't really talked about what a decibel is. A decibel is a relative measure. When I had this in the 70s, 1 dB is a half power point. What does that mean? Or 3 dB, excuse me. 3 dB is a half power point. It means if you have a 3 dB change, you either double the power or halve the power. And that's what the rules, when we get to the rules of 3s and 10s. 3 dB If we had a signal that was minus 6 dB, that means that we would have 50% twice. The first 3 would be 50% to get to 3 dB, and the second 3 would be 50% of what it had changed to get to the 6 dB. If we had 10 dB, the rule of 10 is if it's 10 dB, you multiply by 10 or divide by 10. That's the rule of 10s and 3s. I've got some slides here that demonstrate those in a minute. RSSI, Relative Signal Strength Indicator, is something that the manufacturers put in their antennas to indicate what the relative strength is so that you can get these dB measures. Each of them is going to be a little different, so one to the other, the number of bars that you get, you know, the signal strength, good, bad, indifferent, whatever, or the bandwidth, throughput, data rate that the wireless indicates is based on this relative signal strength indicator. And then the percentage is how much of it we actually have. The milliwatt electrical pressure. Milliwatt or watt is a measure of power, right? 1 volt of pressure, when we talk about pressure, and the way that I think they probably started out with you guys is relating electrical current and flow and voltage and all to a water hose, maybe? Did it do that?
Yeah.
It's very similar. You have so much pressure, right? And you have so much water flow. The water pressure is what the voltage is. The water itself that comes out, the water flow would be the current. And if we opened or closed the nozzle, we would have resistance. So in the electrical generation, we have voltage, current, and impedance. Impedance is a clever term because resistance is linear, impedance really isn't linear. But if we have a voltage, electrical pressure on the wire, measured in volts, if 1 volt push in 1 amp, which is a measure of current, then we have 1 watt. And when we get into electricity, voltage, we talk about high voltage, and everybody's scared of high voltage, right? Not the voltage that gets you. It's the current. Because anybody in you guys in high school, do you have Van de Graaff generators?
No.
Nah. Van de Graaff generator generate about 50,000 volts, go touch it, no problem. About no current. Static. You ever get shocked by a doorknob? It's about, what, 5,000 volts, something like that? No current.
Have you got shot by a taser?
No, and I don't want to be shocked by a taser. Have you?
Yeah. One of the handheld. Well, it wasn't actually.
It's one of the little touchy ones?
Yeah, that's a
Yeah.
taser, and it's like, no, it's stun gun.
Yeah.
There's like
Yeah.
names are different. Stun
Yeah.
gun and taser.
Yeah.
The ones that you touch.
I have been shocked by a capacitor. In high school, I guess we were rude. Charge a capacitor up, start holding hands, you know, one on each lead, and go around until you find somebody in the middle, and discharge the
I've also
capacitor.
been shot by electric fence.
Electric fence, yeah. What, voltage, but not a lot of current, right? Because you don't want to, if you're doing that, you don't want to kill your cattle.
I mean, if you actually hold on to it, you can actually feel it pulsing.
Yeah, yeah, because it's a pulse DC, right?
Yeah.
Yeah. Dog fence kind of does that. But they've got a collar that gets an electromagnetic field, which triggers the collar that's run by a battery, and the dog gets a shot.
Basically, like a little stun gun.
Yeah, a little stun gun. Get their attention. That's all you want to do with it. You don't want to kill them. But you can do those. The current rate, the flow is measured in amperes. How much you're going to get the water flow out the hose. How much you get out is going to be the current flow. And resistance is impedance. And power is actually, when you get power, is actually measured in heat, right? Honestly. Power, because if you have voltage and current and no resistance of any kind, do you actually have any power? And that's why we waste a lot of power at home. We'll digress here. I do, because have you got any devices that get hot? Are you using that power? That's just kind of a waste, isn't it? That's why they're trying with efficiencies.
Like 1,000 watts.
Yeah, 1,000 watts. Regular light bulbs, resistive light bulbs. Incandescent, yeah. They're resistive, aren't they? They've got a little filament in there that glow. Now, how much power does it take to run a 100-watt light bulb? 100 watts! How much does it take to run a 100-watt equivalent fluorescent? 13, 14 watts. You don't really have the heat issue. You get more efficiency. Television's the same way. I have plasmas, boy, they take a lot of power. You can almost heat a room with those things. CRTs also, absolutely. When we got the solid state,
they take the heat from the computer
yep.
and get it upstairs so it heats the building.
Yeah, some people do that, don't they? Well, if you go into and you haven't had, the computers generate an awful lot of heat, and that's one of the big problems in large concentrations in data centers is how you get rid of the heat. And if you look at pictures of those things, they actually have usually chill water cooling running through the racks that the servers are in to get rid of that. We've had a couple of times the cooling unit in the NOC fail, and with as few machines that are in there and we're trying to reduce the number of physical devices, it gets pretty hot pretty quick, and then that starts affecting things. But back to the CRT monitors, yes, they took a lot of heat, they took a lot of power because of the heat. What about now with the LED monitors? Going to be less, because if you feel these things, do they get real hot? And if they don't get real hot, now you've reduced your air conditioning requirement. That's why the rooms are so cold. No, not really, but you reduced your air conditioning requirement, haven't you? All of those things. So they all work together when you can reduce the heat load, reduce the wasted power consumption. Huh? Yeah. Yeah. Amps take an awful lot of power. Yep. Heat your house with them, right? Yeah. Electrical power, a watt's quite a bit is quite large. And when we're talking about wireless access points, the reason we have dBMs is we base it on milliwatts, 1,000th of a watt. So voltage, current, resistance, and electrical power. Power is actually a function. I always say power is voltage times current, right? Kind of. It's really what? E equals IR, it's I squared R. So power changes with the square of the current. That's why when you get into over voltage and under voltage situations, they can do a lot of damage. Because if you have an under voltage, a brownout, what's the power supply going to try to do? Maintain the same power. If your voltage goes down, what happens to the current to maintain that same power? It goes up squared. What causes the damage, the voltage or the current? Current. So that's why, I mean, some of these things, I know I diverge in a lot of these, but brownouts, are brownouts dangerous situations? Probably, except for spikes, can be more dangerous than over voltage situations because of the current's going to go up to try to maintain the power. The decibel milliwatt, the bell is a measure that Bell Labs came up with when the technicians were trying to figure out voice. And a bell was, I think, when it changed by a factor of 10. So that's what a bell is. A decibel is a 1,000th of a bell, right? Decibel is what we're going to use, and the decibel dBm is a decibel milliwatt. It's based on a 0 dBm, because this is the only time that a 0 anything's probably pretty good, right? As you go up or down, you're either going to increase or decrease the power. 3 dB was the, minus 3 dB would be what, double or half? 50%. 3 dB would be double. 10 dB would be, we're going to rehearse this. 10 dB would be 10 times minus 10 dB minus 10, or 1/10 of whatever it started out with. So if we had a minus 10 dB signal on this thing, and we started with 1 milliwatt, we'd have 1/10 of a milliwatt. And the reason we use this is because the signals on the access points are so small that they become kind of unwieldy if you're trying to use watts themselves. There's going to be a chart here in a minute that will show that. Is the decibel milliwatt, because the dB and the milliwatt use different scales, linear versus relative, a conversion is necessary when we move in between the two. Milliwatt's an absolute measure. You can reach out and get shocked by it. A decibel or a dBm, a decibel milliwatt, is something that is relative. One's relative to the other. If we had 1 milliwatt as our standard and we had a minus 3 dB, that would represent 50% of the power. If we had a minus 10 dB, it would represent 1/10 of the power. And when you look at these things, you're going to get something like, minus 50 dBm or minus 80 dBm, those kinds of things. If you get minus 80 dBm, you're probably not going very far. You don't have a very strong signal. And as you get a decrease in the signal strength, the data rate goes down. So that if you get a minus 80 dBm on your 54 megabit per second wireless access point, you may be getting 2 megabits per second. Those do go down, and that's what the speeds we had in a slide yesterday, the different speeds that were available on them. It's not going to be a linear change. You're going to step down in the speed based on what the signal strength is, and the RSSI is going to do the calculation for what that signal strength is going to be. 3 dB, the table 3-7 plus minus 3 dB, and we've already said that. Minus 10 dB, decrease watt to 1/10 of the value. So if we have a minus 10 dB, 90% of the signal's been lost. And if we have a minus 10 dB, minus 20 dB, we have 1/10 of a tenth, which is going to be 100th, right? And if we have a minus 30, we have 1/10 of a tenth of a tenth, which is going to divide by 10 3 times. This is the rule of threes. And this one we have the amplifier, the signal level in is 1. If we have a plus 3 dB, the signal level out is going to be 2, which would put amplifier to the signal level in would be 2. And then we have a 3 dB, again we're going to get 4 out, so you just double it each time. So if we had a 9 dB, it's not quite 10, so we wouldn't use the rule of 10 there, we'd use the rule of 3 times. We double it 3 times. If we had a minus 9, the minus rule of threes, we would have it. This one, they started out with a signal level in of 8, so we didn't have to get into really small numbers. And then we have a minus 3 dB, we get a signal level out of 4 and into the next one of 4, and then we have it again out of 2, so we get an out, and then a minus 3 dB, then we get a signal level out. The reason this becomes significant, when we start doing these things, all of the components can have different influences on the process. Antennas have a gain. I think that, and don't quote me on the number, but I think that I read that those antennas, the little ones that we have on these, have a gain of about 2.3 dB. So amplifiers, Jody's amps have a dB gain. They're going to increase the power when you run the amp, right? Make things really loud. The rule of 10s, same thing, except instead of using 3, we'll use 10. 10 dB. These, again, are not exact measures, but they're close enough. They're close enough to do the calculation for the requirements that you have. As they say, close enough for government work, close enough to be able to answer questions on their tests. This is just 100 milliwatts. We get a 3 dB loss here. The access point, 100 milliwatts. The cable loss, 3 dB, which is going to be, if we get a cable loss of 3 dB, that's a minus 3 dB. So we're going to reduce it by 50%. And then the antenna gets a 10 dBi gain, or 10 dB gain. So a 3 dB loss, half power, we go from 100 to 50, and then we get the 10 dB, we're going to have a 500 milliwatts out the antenna by calculating the power gain or power loss of each of the components. When you buy these things, the FCC rates these, even connectors get rated as a gain or a loss. How much loss do you have through a connector? How much loss do you have through a cable? They have to be rated this way. How much, and antennas we're going to hope are going to have a gain. Although you can have what they call a unigain, which is a one-to-one, you don't get any gain out of it. But you would really want to get some gain out of your antenna. And the term is going to be used for that is going to be passive gain, because we're not actually using any voltage on that thing. Another way to do passive gain, and we'll talk about it in antennas on Monday, is to focus the antenna. It's kind of like a megaphone. If you just speak, excuse me, or cupping your ears. If you cup your ears, you can hear things clearer, can't you? Or megaphone. If you speak through a megaphone, you get an amplified voice, so that you change the coverage area, but you focus the energy in a specific portion where you want to go. And that's going to be the difference between the omnidirectional antennas that we have, and directional antennas are Yagi antennas, Yagis. And what I'm going to have you do to demonstrate those is play a game. How's that? Everybody likes computer games, right? Cisco's got some computer games. We'll use that one to demonstrate. See if you can do these things. When we talk about the dBs versus the gains, this one is a chart starting out with 0 dBm, 1 milliwatt, minus 10 is 100 microwatts, minus 20. 100 microwatts, minus 20, 10 microwatts, minus 30, 1 microwatt, minus 40, 100 nanowatts. It's probably easier to use dB as a relative measure than it is to trying to calculate, remember what all of the actual powers are. The gains, the dB gains, the negatives, and the positives represent actual power. And this is one, this gives a chart going from the top to the bottom, and the 10 to the whatever is 10 to the power. That gives you an idea of what each of those would be. RSSI is a mechanism which the RF signal strength can be measured by the circuitry on the wireless NIC. And this is going to be, it was intended for internal use by the wireless. It's going to be different, a little bit different for every manufacturer. There is no standard to do that. So one NIC may say you're good, and another one may say it's bad if you get it at one of those breakpoints. What we really need to look at is the signal strength that we're getting, and that's going to be based on the decibels, and there are tools that you can get. These phones, James got his phone. Yours measures dB, doesn't it? dB? We'll look at his. We'll go out here and see what kind of signal strength, walk around a little bit, maybe see what kind of signal strength we get around the building for the different ones. I've got a little device that will do that too, I think. Shouldn't be relied upon, not intended to be used. Each vendor may implement an RSSI differently, so there's no real standard for that. If you're really going to measure this, we need to get a device that will actually measure the signal. And those devices cost how much, Trevor?
I don't know, like $5 grand for
$5 grand,
like
yeah.
Up to $40,000.
Up to $40,000.
A lot of money.
See, Metageek actually has one that runs off a USB that's like $200. But, well, yeah, but it's only in for a certain bandwidth, certain frequency level. If you want to do the 2.4 gigahertz, you can do that. If you want to do the 5 gigahertz, you got to get a different one. So you got to buy what you want. It's a lot cheaper than paying $10,000 or $40,000, but you got to be careful as what you're measuring. We have one, but it measures the wrong frequency. Doesn't go into the frequency that we want. Percentage avoided inaccuracies using the RSSI is based on the RF strength. Percentage represents the RSSI for a particular packet divided by the maximum RSSI value, then multiplied by 100. It's just, again, it's based on whatever they do. It gives you a their representation of how much of the original signal they think you're getting through these things. Signal to noise ratio. Signal to noise is going to be a big deal, isn't it? Because we have a lot of noise. What's going to happen to our signal? It's going to degrade or it's going to get lost. And signal to noise, no degradation intended, but what if everybody's talking in the room at the same time and somebody's trying to ask a question across the room? Can I hear the question? Maybe parts of it, but not all of it. Signal to noise is going to be a similar thing. What signal to noise means is how weak can the signal be before the receiver can determine what signal was noise. And Trevor talking about the self-canceling, noise-canceling headphones, what they do is figure out, calculate, find, hear the noise, the ambient noise, and then and now that we've seen that little demo, they just create a signal that's 180 degrees out of phase, and it's canceled. Yeah, noise floor is what this is called. What's the basic, how much noise can you have, the noise floor, so that you can find the signal in the noise itself. Signal to noise, desired signal to undesired signal noise, and the average power level of transmission, and it's again measured in dB. It's a relative measure. Over 40 dB, and this is the signals that we get, or this would be kind of an RSSI. Over 40, excellent, 5 bars. 25 or 25 to 40 dB, 3 to 4 bars. 15 to 25, 2 bars. 10 dB to 15, very low. Less than 10 dB, no signal, be 0 bars. How much signal do we need? And this is a representation of what these would be. The signal to noise in dB is the difference between the signal and the noise floor. The noise floor is the term that you'll hear of it. If the signal is 85 and the noise is 100, the signal to noise is 15. Actually, that would be a minus 15, or minus 85 and a minus 100, not 85. Because when we get these things, as it degrades, they're going to be measured, what we're going to see is measured in negative terms. So minus 85 minus a minus 100 is 15, right? When you subtract a negative, you change the sign and add it. So the signal to noise in this case would be 15 dB. And based on that other chart, that would be a poor signal, wouldn't it? 15, 1 bar, low signal. So what if we didn't have that much noise? Greater than 25 is good. What if our noise was different? We need a lower noise, right? What if the noise was minus 120? What would our signal be? It'd be better. It'd be like, what, 35? No, it'd be 45, right? Because if it were a minus 80 to a minus 120, I can do that one. It's 40. So if it was, no, it would be 35. Minus 85 to minus 120, we're going to have 5 less to be a 35 dB gain. So it would be better. So as the noise, if we can have an environment where we have less noise, then our signal to noise ratio is going to be better. We're going to be able to receive those things. The frequency behavior, radio RF behavior, these are the things that, the terms I've said before, and what they're going to be is reflection, refraction, diffraction, absorption.
I think I'm back in physics later.
Huh? You what now?
I said, that sounds like I'm back in physics.
Back in physics. That's exactly, you are back in physics. Because these are the physics of what goes on. And that's what's going on, right? What causes all that? The physical attributes of these things. And this is one of the common misconceptions. The RF signal goes out from the antenna in a single signal that takes it in a direct path to the receiver. That doesn't happen. We've talked about multipath. How does it get there? It bounces around. Different things are going to absorb it different ways. even from the one in the back of the room up here, there's different materials that it's going to go through, or from this antenna back there, different materials. We've got the monitors, we've got the chairs, we've got the walls that can bounce off of. We've got people that can absorb some of the signal. All of those things are going to affect what actually gets there. Not just the RF signal, multiple copies, all the things that we talked about, wave propagation in different ways. So when we get these things and the top is the incorrect, goes from point A directly from point A to point B, that's not going to happen. The correct way is the one that shows down here bouncing around all these different places. And if it's going to bounce around, what's going to happen to the signal? This one that leaves at the same point at the same time. What happens if two cars leave at the same point at the same time and take different routes? One of them goes on the interstate and the other one goes on. One's going to get quicker than the other. Same thing's going to happen here. So we're going to have these things. And these are the pictures. Absorption. Absorption occurs when the RF signal striking the object is absorbed into the material, disappears. It doesn't pass through it and it's not reflected off of it. Concrete, wood, asphalt are things that are going to absorb signals. Reflection, opposite of absorption, it's going to be reflected off. And in reflection, the angle, this shows here, the angle of incidence and the angle that goes in, the angle that's bounced off, the angle of incidence is going to equal the angle of reflection. Smooth surfaces are going to, so these are smooth surfaces in here, right? So they're going to reflect some off. Some of it's going to go through the wall. Some of it's going to be absorbed by the wall, drywall. And you can find the absorption properties of the materials. Scattering, it's going to be irregular surfaces are going to scatter these things. So those things. Irregular, and one of the ones that they show is, it's like the, the glass balls, and they shine the lights on them, and it goes off in all different, you can get different bouncing around of those things. You get scattering of the light waves. Refraction, and this one shows some reflection and some refraction. The incoming signal, some of it's reflected. The refraction is when it changes the angle. And you've probably seen this in a restaurant when you put a straw in a glass of water. Looks like it's bent. Looks like it's in two different parts. That's because we have different densities, two different materials, different densities of the different materials, and that's what happens in refraction. That's exactly the theory that we'll go in a different media. That's what fiber uses in order to keep the signal in. It's actually refracted. The term that they use is total internal reflection, but it's actually refracted. It's bent back into the media. And we're going to get multipath because the deeper it goes, you're going to have a lot of different paths on those as we go through those things. So it moves from one medium to the other. We're going to get refraction. And again, straw, pencil, and a glass of water is what that's going to look like, what those are going to be. Diffraction is actually a bending of the waveform when it strikes an object. And this one's showing, and this is an aerial view. If you're looking down, we're sending this signal out. It hits the building rooftop. Part of the signal is bent. Part of it will continue on its original path. So what each of these things can do, each of these represent what different objects can do to change your signal path, to create your multipath. When are the signals actually going to get there? Attenuation. Been there, done that, got that one, right? Loss of signal strength. As it gets smaller, it's kind of like a voice. How far does voice go? If somebody's talking, having a conversation, or if somebody's talking to somebody else and you're on a football field, if they're at one goal line and you're at the other goal line, are you going to hear it? What if they yell? Are you going to hear it, but it's going to be faint? That's attenuation. That's exactly what attenuation. Huh? Some people can project pretty well. And yeah, oh yeah. Well, what do cheerleaders use? They use a megaphone, right, to focus the voice. I'm hard of hearing. What do I hear? What I want to do when I want to hear something on the TV? I put my hand up to try to capture the signal. All of these things in voice really affect, because voice, this is an electromagnetic wave, isn't it? It's different part of the spectrum. But we're doing a similar thing here. Attenuation's the loss of signal, and the further we go away, the smaller the signal's going to get. Wrong one. 2 phenomenon, free space path loss, and that's a term they want you to know. All that says is the farther you get away, the lower it's going to get. Delays spread the difference in time in multipath signals that reach the receiver. And they use not a result, and the free space path loss is not a result of absorption, reflection, scattering, or diffraction. All those things that we talked about. So that means it's just out in free space, and it's going to, actually what it does is spreads out, right? And as it spreads out, it's going to get weaker. So free space path loss, and I've seen a couple of books that do this like a balloon. When you blow up a balloon, what happens to the skin of it? Gets tight, gets thinner, doesn't it? Does it get thinner? Because you get it just before it's going to go boom, you can kind of see through it. You can't see through it before. So free space path loss, FSPL, is represented by that. Multipath delays, I guess we've done that enough, but there's lots of different things can cause multipath, and this one's showing a bunch of reflection. I expected you'd get some absorption from that couch too, wouldn't you? All of those factors are going to go into these things. Well, leather couch, yeah, could be. What about a rough ceiling? We're going to get some scattering from it, perhaps, aren't we?
Yeah, material gets absorption.
So the absorption, and there are tables, and I don't have one here, but there are tables to tell you what the reflection properties are, what the absorption properties are for the different materials. What are the ones that we need to be concerned about? Drywall? Cement, maybe? Metal? Maybe metal, but yeah, tiles, light fixtures. We'll probably get some reflection out of these light fixtures. We'll also get some interference out of these things too, right, because they're fluorescent. Not a whole lot, but you get some out of them. Don't set your wireless access point on top of your fluorescent light. I know somebody that, I had a student that did this. Well, wireless isn't working very well. Where is it? It's on top of the refrigerator under a fluorescent light. That works out real well. All this free. Huh?
That makes it surprise my router.
Oh, yeah.
I got big steel mill racks for all the
Yeah. Yeah, steel racks. But we were playing around in here, and these signals really do travel pretty well, don't they? We took a computer case and put it over. It had a bunch of holes where the hard drives and stuff, and they had a plastic front. Didn't change the signal strength very much up here. We're relatively close. If we were further away, and I want to try the same experiment maybe next week where we take and put it in a different room, do similar things and see what happens to it as we get farther away. So gain, the positive difference between amplitude between the two signals, how much we're going to make the signal bigger. Two different types of gain. We're going to have active gain and passive gain. Active gain is where we actually change the amplification by using input power. That's where we're going to get that heat. That's Jody's studio here. He's going to plug it in, he's going to turn the power up, and he's going to pay the electric bill. The other type gain we're going to have is passive gain, and that goes back to keep talking about when the cheerleader uses the megaphone. They're going to yell, but they're going to yell at the same decibel level because sound's measured in about decibels alpha. What do they do in order to talk to their crowd, not the other crowd? They use that megaphone. So the whole yelling that they do into the megaphone is going to be focused. That's going to be passive gain. You can do the same thing with antennas. If we took an antenna, instead of sending all of the energy out in all different directions and only send it in a single direction, and we call that a directional antenna, right? We're going to focus, Pringles can, we're going to focus the same energy that we've produced in that smaller area. So it's going to be an amplified signal. But we didn't have to pay the electric company anything to do that. Passive gain. It's not free. We still produce the same amount of power, but we focused it. We used the power where we wanted it, not every place else. The upfade and downfade are what these things are going to be called. The end result when we amplify is upfade. The end result when we get a reduced signal due to multipass is going to be called downfade. So with that, RF, does it make any more sense why some of these things do what they do? Hopefully after you get done with them. Electromagnetic waves, the spectrum, all different sorts of influences on the signal that we have as we do those things, the reflection, refraction, absorption, and those things. Questions? Going once, going twice. Now, you got some activities to do, so we can do those.